Welcome to the Yaka Digital Network. Today, we are tackling a critical topic in Senior 3 technical drawing, loci. Take a look at this classroom setting. Mastering the precise geometry taught on these chalkboards is the first step toward understanding complex mechanical motion. That motion powers everyday life across Uganda. Outside local shops, like the one in this photograph, you will see motorcycles and vehicles that rely on specific mechanical linkages to function safely. Look closely at this spinning metal gear. Smooth power transmission in those engines requires gear teeth shaped with exact precision. Those shapes are built entirely on the mathematical principles of loci. Specifically, we are going to draw the locus known as an epicycloid. By following today's methodical steps, you will construct a perfect continuous curve from scratch. On this drawing board, you can see the required setup: a T-square, set squares, a compass, a protractor, dividers, and crucially, 2 types of pencils. You must have an H pencil for light construction lines and an HB pencil for your final curve. Setting up your workspace correctly and executing these precise steps guarantees top marks on your UNEB assignments and provides the exact geometric foundation you need for real-world mechanical engineering. This animation shows an epicycloid, the exact path traced by a point on the circumference of a generating circle rolling along a stationary base circle. To roll without slipping, the highlighted blue arc segment must exactly match the generating circle's red circumference. Because you will divide your generating circle into 12 equal parts, you need to find the exact angle for each matching step on the base circle. Here is the formula. Theta equals the radius of the generating circle divided by the radius of the base circle, multiplied by 30 degrees. Before moving on, pause the video. Take the specific radius values assigned in your problem and calculate your theta angle. Completing this calculation accurately is crucial. If the spacing is even slightly off, your final curve will fail to close perfectly at the end of the rotation. Now we begin the physical construction. Pick up your H pencil. You must use a hard lead so all your initial layout lines remain extremely faint. First, draw your stationary base circle using your assigned radius r. Next, draw your generating circle using radius r. In this diagram, you can see how the smaller generating circle rests perfectly on top of the base circle, touching at exactly one tangent contact point, labeled P. Establishing a perfect single-point tangent at P is the physical foundation for the rest of your drawing. Any overlap or gap here will distort the entire mechanism's movement. Step 1 of mapping the movement: divide your generating circle into 12 equal slices of 30 degrees each, numbering them sequentially from the contact point. Step 2 is mapping the trajectory. Looking at this diagram, a new faint outer arc originates from the center of the base circle. To draw this on your board, open your compass to a radius equal to r plus r and sweep a large arc passing through the center of your generating circle. Using the theta angle you calculated earlier, measure and mark off those specific degree increments along the edge of your base circle. Project straight lines from those angle marks directly up to your outer center arc to establish 12 distinct center positions. You now have 12 specific points. These act as a time lapse, showing the exact physical location of the generating circle center at every step of its journey around the base. To guide our next step, draw straight radial reference lines outward from the center of the base circle, passing through your 12 center points. Maintain very light pressure with your H pencil. The page is about to become heavily populated with lines, and keeping them faint is essential for clarity. Place your compass point on each of your 12 new centers, C1 through C12, and draw the generating circle at every location. Notice in this diagram how the 12 faint blue generating circles populate along the center arc. The resulting web of overlapping circles looks chaotic, but do not worry. This is the highly organized framework required to track the locus of our moving point. Now we extract our curve. Take your dividers and go to the very first generating circle you drew. Measure the horizontal distance from its vertical center line out to the first intersection point on its perimeter. As the divider tool shows here, transfer that exact horizontal measurement onto the corresponding projected circle further down the arc, marking the spot with a small red dot. Repeat this exact transfer process for all 12 positions. At each step, measure the horizontal distance on the original circle, Then plot that precise distance onto the corresponding moving circle with a light dot. You have mapped the path. Pick up your soft HB pencil for the final step. Carefully connect your plotted dots. Use a French curve or sketch it freehand, linking the red dots to form the arched shape of the epicycloid. This bold, continuous line represents the precise mechanical path a gear tooth will follow. Heavy industrial machinery relies on this exact geometric curve to ensure gears mesh smoothly and do not jam. Inspect your final drawing. Check the starting point P. If your construction spacing was accurate, your bold curve will return perfectly to that starting tangent point after the 12th division. Take a look at this completed drawing. A successful exam paper will have this clear visual contrast. The complex web of construction lines remains incredibly faint, while the final epicycloid curve stands out dark, bold, and perfectly smooth. Precision in these geometric shapes yields reliable mechanical components. Understanding how to calculate and track these complex linkage mechanisms separates adequate technicians from master engineers in Ugandan industry. For more UNEB format assignments, detailed step-by-step video tutorials, and technical drawing resources, visit the Yaka Digital Network website. Keep practicing your loci, and we will see you in the next lesson.